Yeah, I have to say, it would have been nice to have come down to Imperial. It seems a while ago since I did my PhD there. And as David said, that my postdoc with them was across the road at UCL. And then I sort of travelled a bit before landing in Cambridge. Let's see, let's get the screen going, and hopefully everyone can see that. So I'm at the Institute of Astronomy, and I've stuck a couple of logos up. I won't put logos anywhere else really, but let's see. The Is Gaia logo, and the white, yellow, blue one is the DPAC, which is the Data Processing and Analysis Consortium. And then funding that we get to support this activity is coming mainly from the UK Space Agency in the UK, and also a little bit from the Science and Technology Facilities Council, STFC. And I'm a little bit, just a couple of words about me. There's an image, by the way. This is a graphic that we drew up for the last Gaia data release, and there's an image of Gaia itself. Let me just that. So let's see. Okay, I sort of got an introduction there. The bit I had a decade on La Palma at the Royal Greenwich Observatory, the Isaac Newton Group of telescopes. That's an image I took a little while ago of the William Herschel telescope. You might have seen La Palma in the news recently. September to December, they had a pretty impressive volcanic eruption going off on the island, and I looked it up on the map, and that was about 8 miles away from where I used to live for a decade. So that was quite interesting. And I'm still involved with projects that are emerging, going to be deployed on the William Herschel telescope. Got a spectrograph being built at the moment, and it's going to be commissioned in June, I think. Yeah, we're going to start June, so I'll be out there in June, COVID restrictions permitting. There's a graphic at the launch event for Gaia. So I've been a member of the Gaia Science team for quite a number of years now, since about 2007. So that's the body that sort of coordinates the science of Gaia at the ESA level. And also I dabble in some projects with colleagues in Cancer Research UK. So I'm involved in transferring some of the image analysis techniques we use in astronomy and deploying those for analysis of breast cancer tumours, building up 3D annotated maps of breast tumours. In fact, very similar to what we're trying to do with Gaia and annotate the stars in our galaxy. Here we're trying to annotate the cells in our body, if you like. But anyway, I won't talk about that. There's another talk, but pretty interesting. That's something you might hear about in the news in a not too distant future through the Grand Challenge program. Okay, let's say a little bit about why we decided to build, and how we got the funding, if you like, to build Gaia. And I'll come to the history of that in a bit. But here's a couple of graphics really showing some ideas that we've got, and our understanding through modeling and investigating the galaxies and the cosmos and the universe more widely. It's trying to build up an understanding of how our Milky Way formed. So at the bottom on the left, you see sort of look down at a spiral galaxy such as our own. So the galactic center there and spiral arms. And how did that actually get to be? So if we look back, the trees, if you like, it's almost like a tree of life for a galaxy. And the idea is that there's a hierarchical evolution model. So it's the idea here is that smaller galaxies merge and accrete to form larger galaxies. And what we're trying to do is see if, by looking at the stars that we see in our galaxy today, we can get a better picture. And this is a sort of a subject named Galactic Archaeology, because we're studying our stars to look for evidence of where those stars came from. So what we might try to do, for instance, is try to find stars that are relics left over or are derived from stars which were associated with, for instance, the three galaxies just above the bottom representation of our galaxy there. Now, there are a number of cosmological models. There's a lot of simulation going on. Here's some graphics of a recent summary from 2020 showing dark matter n-body simulations that are used to sort of simulate how galaxies at the cosmic scales are formed. And then there are techniques that can bring in not just the dark matter, but the baryonic matter, so the sort of matter that we actually see forming our galaxies. So what we're trying to do really is use these to help us understand the galaxy formation. And with Gaia, what we want to really do is start to investigate at great detail the stars within our galaxy. And what's really the most important thing here is that we're able to measure some fundamental properties about those stars, because when we look at the stars, most stars, we cannot get basic information such as distances to those stars, or at least not accurate distances. And Gaia's mission is basically to measure distances of a large sample of stars in our galaxy so that we can accurately place those stars in the galaxy. And here's a graphic of some of the components of our galaxy, and I'm hoping that that I should say, if you do have any questions, you know, and something pops up, do interrupt. This is showing a schematic of some of the major elements of our Milky Way, or a typical spiral galaxy such as ours. And you can see here a location where the sun is indicated out in the spiral arms. The distance to the galactic centre is about 8.5 kiloparsecs. That's 8,500 parsecs, which is 20-odd thousand light years, light travel time to get to the galactic centre. Looking edge on, you'll see a sort of a halo of stars with some dense globular clusters embedded within that, a disk structure, and a more condensed region in the bulge. And what we really want to do is sample stars in all of those areas. Now, why do we want to do that, and how do we actually say, for instance, a star is a low mass star, or a high mass star, or a hot star, or a cold star? Well, what we want to do here is measure the star's position, a few basic parameters, which is basically luminosity, so brightness against color, which gives you an idea of temperature. And to get absolute values for those, you really need the distances accurately. Once you've got the distances, accurate distances, you can do this sort of thing. So this is showing a visualization from the second data release of Gaia back in 2018 now. So this is the star field that you might see. This is a sample of about 60,000 stars within two and a bit thousand light years of the sun. And what we're doing here is we're collapsing the stars from in terms of color. So the hotter stars, the bluer stars, are on the left, and the redder stars are on the right. And once we've got the distance, we can measure the apparent brightness, and then through the distance, you can scale that to determine the absolute luminosity, the absolute brightness. So the axis, the y-axis now, gives an indication of the brightness. So in the top left, for instance, you see bright, hot stars, and in the bottom right, you see fainter, redder stars, so lower temperature stars. And you'll see that the way that what looked like a fairly homogeneous set of star objects in terms of position on the sky are now nicely aligned in set positions within what is called the Hertzsprung-Russell diagram. And you'll see, for instance, to the bottom left, there is another track of stars which are fainter but bluer, and these are actually white dwarf stars. So the bulk of the stars lie along the line, the yellow sort of objects, which are the so-called main sequence stars. You'll see there's a turn-off where the giants go, and then basically things are in the top right when they're at the end of their life, and they move across to the top left and then eventually cool down and die off as white dwarf stars. But this is how you actually order stars. Let's see, so we'll go to the next slot. So once you've able to position stars accurately on the Hertzsprung-Russell diagram, and really you need the accurate distances for this, you can then sort of locate the different types of stars, and we have names for these stars, the different types of stars or different stages of the evolution of the actual objects. And on the right, there's an image there naming some of the sort of more known stars that we can actually see in the night sky, and sort of saying what they are. Now, in terms of measuring distance, well, if we want to measure a distance now, I mean, it's even if you're it reminded me the other day actually, sort of fitting a new carpet, and then somebody comes along, and in the old days somebody used to come along and get a tape measure out and measure the distance of the room, and now it's a little radar signal measuring the distance. So, for instance, if we want to measure the distance to objects such as, you know, the moon or so, we're using some sort of radar LiDAR type technique where we're bouncing a signal off that object and measuring the return time. So we can get a direct measure, but of course you can only do that for very nearby objects, mainly in our solar system, nearby objects in our solar system. If you want to go a bit further, another direct measurement is the so-called parallax technique, which is basically taking advantage of the fact that, and you can do this easily by yourself. If you put the finger in front of your nose a little way, and then look at look at your finger against the background objects, you will see that your finger appears to move against the background objects which are further away, but your finger will move left to right depending on which eye you're looking at. And if you move your finger backwards and forwards, closer to your nose or further away from your nose, you will notice that the apparent motion of your finger against the background objects will get less the further away your finger is. And this is basically taking advantage of parallax here. Now, the Earth, of course, is orbiting the Sun. So at 1 astronomical unit, so we have a baseline. So if we observe a star field, say in the 1st of July, and then observe it six months later in January, we get a really quite long baseline of our observation field. And we can use this to measure, we can then measure objects, the movement, the apparent movement of an object against stars that are further away. Now, the nearest sort of star that we can measure has got a parallax of about 0.7 of an arc second. So that's quite a small angle. An arc second is 1/3600th of a degree. But that we can measure with various techniques, and that's sort of gives you an object of let's see, what's always forget the exact number. It's a couple of light years away. But if we want to go to more interesting distances, we really need to get parallaxes down to precisions and accuracies of thousandths of an arc second. And basically, Gaia is giving us parallax accuracies, and precision on the errors are down at the micro arc second level, which enables us to measure motions of stars at significant distances and out to basically out to the edge of our Milky Way or to the center of our galaxy. Before Gaia, we could only really measure objects up to about 100 light years away. So we had a very small direct measurement of objects. After Gaia, we can push that out to actually getting direct measurements of star distances way across large chunks of the Milky Way. And this enables us to then also better understand and link the various secondary techniques that are used to measure distances to objects out to cosmic distances. So there's a whole distance ladder, but most of those are underpinned by the direct measures of nearby objects. And one of the crucial techniques is this period luminosity of Cepheids. Cepheids are very bright objects, and you can use those as a relationship between their period and luminosity. So if you can measure how the period of their brightness going up and down, you can relate that to their absolute luminosity, and then you can get a distance of a further away object. But you need a good calibrating sample. And before Gaia, we didn't have many objects, many Cepheids that we could directly measure. Now we have thousands, which is giving us a much better ability to measure distances to galaxies out of sort of tens of megaparsecs regime. And that really helps improve a lot of our understanding of cosmology more generally. And this is measures of the Hubble constant coming from that. So here's a little graphic of how Gaia's working. Gaia's orbiting at L2, so it's really just a little bit further out than the Earth there. And this is what a star motion might look like as you go round the sun over the year. And here we see a star field and how this appears. And this is the motion. The proper motion is real motion of the object, and the sort of tighter spiral is the actual parallax due to our motion around the sun. Okay, so how precise is Gaia? Well, I mentioned arc seconds and milliarc seconds, which is as good as we had before. Well, now we get to microarc seconds. Gaia accuracies are down at the just over a few microarc seconds. And what does this actually tell us? Well, it means that if we're sitting on the Earth and we're looking at a euro coin or a 10p coin on the moon surface, you would actually be able to resolve that. So that gives you an idea of how precise the measurements are with Gaia. And it sort of enables you to, you can watch a hair grow, for instance, with this sort of precision. So this is quite interesting. This is the view from a euro on the Earth, actually. Because I'm looking ahead, you see, when we've got a nice station on the moon when we're worried about these things. Okay, and here's a graphic of Gaia itself. So this is the internals of Gaia. Gaia is basically two mirrors, which are about 1.5 meters each, rectangular mirrors, and they are able to combine their fields. So they're looking out two different directions all the time. It's scanning at 60 arc seconds per second, continuously scanning the sky, observing objects to about 20th magnitude, and observing the whole sky in a few months through this Gaia scanning law. And on board, it has a very large set of CCDs, largest camera in space at the moment, and a set of astrometric CCDs where it's getting a white light brightness measurement, which is enabling it to measure positions of objects and just get a bright light magnitude. And then it's got a low resolution spectroscopic spectrometry capability, which gives magnitudes, spectrophotometry in the optical region, in the blue and the red, and this enables us to classify the objects. And also there's a higher resolution spectroscopy around the calcium triplet region, which enables us to get some quite detailed chemical abundances for the objects for many of the brighter stars. Okay, and here's a closer up view of the camera. This was an image put out by Astrium at the time. They're now Airbus Defence and Space. So 106 large format CCDs here, and this was really an impressive piece of engineering. The CCDs were actually manufactured in Chelmsford by E2V. It's E2V Teledyne now. There's a large amount of data that comes from Gaia. This is a screenshot from September or so last year. To the distance, there's a information status page that can tell you these sort of numbers. 1 trillion observations were reached back in 2018. It's just about 2 trillion observations now. So there's a lot of data, a lot of photometric measurements, spectroscopic measurements, transits, and so forth. we get about 80 gigabytes of data downlink per day. And there's a large number of scientists and software engineers that have put together a processing system to analyze the data. And there are processing centers across Europe. We're in the UK responsible for the photometric processing. We also are significant contributors to the spectroscopic processing and also data release and so forth. So we're a major player in the effort. And just sort of worth sort of pointing out that science is really done by people. So in the background, there's a large number of scientists. As I say, this is from a consortium meeting a few years ago now, showing a large chunk of the engineers that are, and scientists that are involved, and the astronomers that are involved. And we've got some images there of the processing executive science team. Some of this is a promo showing that there's a good gender balance in Gaia, and student training activities that we've had around Gaia as well. So it's nice to sort of reflect on the input from these really, I would say, very clever people. Here's a nice. Let me just check that I've got this on. I think I have. Yeah, nice little graphic. It just takes a second or so that ESA put out, which is showing Gaia to launch. So this gives you an idea of the scale. That's the sun shield. You see the ESA engineers work at double speed, really. And the two telescopes are within the container. It's about 9 meters across. This is getting ready to put it into the Soyuz frigate launch final stage in the fairing. And this is adding the logo. This is the Soyuz frigate being prepared. This is the Russian bit. So the Russians are good at rockets. And this is in French Guiana, South America. And the rocket's being put to the launch pad. And then they bring the housing over this to bring up Gaia. Gaia gets put on the top. And then when the weather clears, nice clear sky.
3, 2, 1, top, décollage.
And that's the launch. Hopefully we'll see that. It looks like my computer is not completely showing that whole thing, but anyway, there we go. Right. That's that. Next slide. Okay, so this was launched back in 2013. First commissioning image, always a relief to get that. We'll have to see some of those, I think, from James Webb in a few months. That'll be exciting when they appear, June, July. Right, and I also note that it seems a while, but it had a nominal 5-year mission, and that's successfully completed back in 2019. And that was exactly 50 years from the launch of Apollo 11. And the rockets look about the same. It's quite amazing, actually, what they could achieve back in the 60s. Where is Gaia? Gaia is at L2, so you will hear about L2 because this is the Earth. This is about 1 million miles, 1.5 million, 1.6 million kilometers out to the second Lagrangian point. Fairly quiescent location. Gaia's on a large orbit there. Actually, its orbit is 600,000 kilometers. It's quite a complex sort of orbit around L2. But that's where it actually lives, so it's out there. Now, how's it actually observing stars? Here we see a star field. This is about, let's see, this is about a minute's worth of data coming across here. So there's about 110,000 stars that are observed in the strip of CCDs. So this is coming from the 60 arc seconds per second scanning rate. So we're scanning of order 6 million objects in the hour. In the hour that I'm talking, Gaia's up there, it would observe about 6 million objects. It's about 150 million a day. So a large number of objects a day, and it scans the whole sky in a few months, and we just keep repeating. So every object gets observed. In 10 years, every object will get observed, probably getting on for 150 to 200 times. It depends a bit where it is on the sky. And 2 billion objects in the catalogue by final release. 2 billion, if you counted that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., that'd take about 60 years to count. So 2 billion objects, a large number, and it's about 1% of the total stars in our galaxy. So it means that we get a nicely annotated sample where we can measure the temperatures, fluxes, colors, some chemistry, positions, motions, and so forth of that set of objects, which enables us to really get a good census of our Milky Way. So this is great. The last data release, December 2020, we've got another data release coming up in a few months, actually, in May, June, probably June 2022, which will bring in lots more data products and improve everything. But this was the last catalogue, and this is what I'll talk about a little bit in the next 20 minutes or so. So this was the first data release. This was September 2016. This was based really only on a few months of data, and you can see quite clearly in this the imprint of the scanning law. So some areas of the sky there were more observations, and you'll see the sort of brighter patches and the sort of certain rings where basically there was less observations. On the top right, for instance, you'll see the sort of striping where there are some fields which were very poorly observed. So there were quite a few sort of artifacts, if you like, just due to the lack of data that had been obtained at that time. But even with this first data set, we were able to put out a first catalogue with distances of the brighter objects of about 5 million objects, which were a massive improvement on what we had before. Because the first catalogue we put out 5 million objects. The previous Parallax catalogue that was the gold standard at the time from Hipparchus was about 110,000 objects. So here we significantly increased that and improved the accuracies on the parallaxes. And here's an annotated diagram showing some of the features that we can see: the LMC, the SMC, for instance, large Magellanic cloud, small Magellanic cloud, towards the galactic center. And every dot really is a globular cluster or is actually a feature. You can see the obscured regions. It gets more complicated in the galactic center. So these are source counts. So each pixel here is actually it's represented the pixels that are displayed are actually adding up, because there's many more objects than you can resolve here. They're adding up the sort of number of objects within one of the pixel in the image. So it's not actually showing brightness in the sky; it's showing the source density, source counts. So here you can see quite clearly the Magellanic clouds, but also on the bottom left you can see the Andromeda galaxy there, M31, for instance. Now, if we go to DR2, this sort of doubled the amount of data that was released, and you'll see that the artifacts from the scanning law have been reduced. This was the release from 2018. And if I zoom in, and the fact that we've got more data, you can look at the detail, for instance. So here's some galaxies, M31, M33, I think. And you can quite clearly see giant, bright, these are the OB supergiants, so-called, the brightest stars in those galaxies, but they pop out pretty nicely. And that sort of data enables you to measure. You can get proper motions of those, and you can measure the rotation curves in those galaxies directly. Very nice results from DR2. Here's the color. DR2, we released I said we had the blue and the red photometers, and it gives us an ability, and then combined with the G-band broadband fluxes, we can actually assign colors to all the objects. And here we're actually displaying this, each of the pixels in the image counts the fluxes of the objects. So here you'll see, because we're counting flux now, so the brighter objects get more weight. You'll see that M31 has sort of disappeared because we're not plotting counts of objects now. We're actually showing the brighter objects, but you can see more structure and detail in the Magellanic clouds. Large Magellanic clouds, for instance, bluer, hotter star-forming regions there nicely pop out as white, and then you can see the sort of cooler yellow, redder objects in the behind the dust in the towards the galactic center. So if we sort of zoom in a bit on some of this is the EDR3 release. So this is the latest state of the art. You'll see a lot more features popping out here. This is because we've got more data here. We've got about 34 months of data. Getting on for 3 years of data are contained within this graphic. This is 1.5 billion stars represented in this image, this whole sky image. And I should say this is at the resolution of Hubble. So that Hubble would be a dot. The field of view of Hubble Space Telescope is about a dot on this scale. And here we get the whole sky resolutions of about 0.15, 0.2 arc seconds. And just zooming in on a bit of detail, this is the Ophiuchus molecular cloud, giant molecular cloud. I'll just go back so you can see it. It's towards just above the galactic center. And you can see the molecular clouds and the obscuration in there, and some of the sort of star-forming regions. And if we zoom in on the large and the small Magellanic clouds, you can quite clearly see the stellar populations in those objects, and of course you can directly measure rotation curves, distances, and so forth. So Gaia Science, I'll touch on a few some of the highlights. I mean, there's massive amount of science coming out of Gaia. I just did a check last night. I think there are about 6,050 papers that are referencing Gaia data and Gaia data products that have been peer reviewed since launch, and this makes it it overtook every other ESA mission in terms of productivity. The papers per year rate is now overtaken Hubble. It won't be long before it is absolutely the most scientifically productive mission, certainly for ESA, and I think it's going to overtake total papers of Hubble in the not so distant future. And the science, well, basically it touches on all areas of astrophysics, from nearby solar system, asteroids, structure of stars, formation of the Milky Way. You can, from the properties of motions, you can measure the influence of dark matter, and you can touch on fundamental physics as well. We can measure the acceleration of our sun towards the direct measurement of our sun around the Milky Way center, which I'll touch on. So here's a little representation of 40,000 stars that are, let's see, is it going to start? Yeah, 40,000 stars. These are brighter stars, nearby stars. Each of the arcs is 80,000 years, and we're looking forward 1.6 million years. So this, because we've got the proper motions, we can predict where they're actually going to go, where these stars have come from. We can move them forward, we can move them back. And you can see here that some stars are closer by, the ones which have got longer arcs, if you like. You could see, I might replay that actually, it's quite interesting. You'll see some stars which really got high velocities. You'll see one shooting across the screen, bottom, sort of from center to bottom left, so-called high velocity stars. And some of these have been tracked. I think one went by there, and I think I saw there's one going there. I think one comes in really quite quickly over here. And some of these are stars which we think are actually being captured from other galaxies, external galaxies. And we can also, from the star motions, we can see, we can look for groups, moving groups, so-called, to help work out if they've come from a common sort of birthplace and so forth. So there's a lot you can do with that. once you've got the accurate distances, you can really say.
Nick, I think we've lost the picture. It's just come. We lost the end of the movie.
All right, okay. Well, never mind, because I showed it twice, so that's all right.
That's all right. Yeah, we saw it the first time.
Yeah. I'll carry on. So here we are. When you've got very small error bars on the points you plot on these Hertzsprung-Russell diagrams, and you've got a lot of points to plot, you can start to investigate in some detail the star sample type. So here's showing from, I think this is the DR2 paper, showing how with the really small error bars, you can start to look at the white dwarf sequences, for instance, to differentiate between different types of white dwarfs directly from the Hertzsprung-Russell diagram. You can look at various and pull out various types of stars. The red clump stars are very important giant branch stars that astronomers use as standard candles for measuring distances of further away galaxies, because these tend to be quite bright, so you can identify those quite clearly. They've got a specific place in the color diagram. And here we see the stars plotted against accurate temperatures and so forth. With the motions of stars, proper motions, and knowing where they've come from and what's fitting together and looking at the sort of common properties, we've been able to, well, one, find bridges of stars in the Magellanic Cloud. So this is showing how the large Magellanic Cloud is accreting the small Magellanic Cloud, and you can see this almost in real time. And you can see bridges of stars linking to, so stars that are being ripped off the large Magellanic Cloud from the small Magellanic Cloud, and that just pops out. Here we're seeing the disruption of clusters, which can then be used to map the dynamics of the Milky Way. And here we're seeing the so-called Gaia Enceladus, was jointly discovered in Groningen by a Groningen-based team and also a Cambridge-based team. The Cambridge-based team went for the more snappy-sounding Gaia sausage. And this is a direct measurement of a massive dwarf galaxy that was accreted into the Milky Way some number of, I think 8 or 9 giga-years ago. And this is one of the most recent accretion events where our galaxy had accreted a significant external galaxy. Let me just yeah. Here we're showing how we can use what we call the Doppler effect to see where stars are coming towards us or moving away from us. And here we're showing the radial velocities of about 7 million stars, and the blue parts of where the stars are coming towards us, while the red parts show those moving away from us. And what we see here is due to the fact that the sun orbits the Milky Way, and we have this sort of differential effect. So we can see this, use this as a direct means of showing how the sun is orbiting the Milky Way. Another nice release and a sub-catalogue of the Gaia sample that we put out with the data release 3 was the Gaia Catalogue of Nearby Stars. And this is a comprehensive and fairly complete sample of about 300,000 stars within 100 parsecs of the sun. And it significantly increases the number of stars that we've got accurate measurements of, and it's an almost complete number of the stars down to 20th mag within 100 parsecs of our sun. Once you've got these accurate measurements of this sample, you can then do some nice. I need to get to the next slide. Here's a graphic of those 300,000 stars. And this is showing the sun. I should say, I'll give a link to the software that's used to generate this. So it's the sort of thing you can do at home if you want to go and get the software at the end. So this is showing the sun, and we're zooming away now. We're zooming out from the sun. You saw the planets in the solar system go by, and now we're sort of seeing the stars in this 100 light year sample. We're zooming out so that we'll be able to see the volume that's contained within the 100 light years. And now we've got very precise positions of these. So this is sort of visualizing, if you like, moving around our 3D map of the stars, and we can move around within the volume. The color coding, so white, blue are hotter objects, red are the fainter objects. And we can see also, because we not only measure the parallaxes, distances, we measure the proper motions. So these are the vectors, so the bigger, longer arrows are faster moving objects. And if you see objects that are moving sort of close together with the same sort of properties of motion, then we can sort of relate those as having some sort of common birthplace or pop-out binaries. So here we're going to look at some objects which are color-coded in yellow, which are sort of objects which are related to each other, that are binaries that are orbiting each other. And we can have a look at some of these. We can zoom in. Some are wide binaries, some are wider binaries. And we're going to get a little move around here. And we can see that with these, you'll see here, for instance, the vectors are the same direction, same length. So that we can pop these out. And we've discovered quite a number of new binaries by being able to just look at their motion properties, not having to use any other techniques. And here I just zoom into the Hyades cluster, and these are going to get color coded. This is a cluster that was formed about 600 million years ago, which is quite recent. This is a young cluster. Here they are. And these stars are pulled out from the background stars because they've got the same motions. You'll know other field stars have got directions pointing in different ways. So here's a way that you can use their orbital and motion parameters to allocate the stars to that cluster. So we found some more stars that were related to that cluster. The brighter ones were already known, but some of the fainter ones were not. And I will skip this now because this is showing the 100 light year sample, the 300,000 objects or so in the volume, and we're going to zoom out a little bit, and it sort of shows you where it is. That's the sample. This is the larger sample in the Milky Way. These are still Gaia objects, and then the purple blue image is an artist's impression of the Milky Way, and this is where that sample would be in the Milky Way. Right. Okay. And that sample, we can also see where those stars are going to go. So this is looking ahead where those objects will actually travel in the next 500 million years. So this is the stars shown there, and then some of these are going to have high velocity orbits. Top right, you'll see the time. You'll see the ones that escape the galactic plane and form and go into the halo. These are the orange objects, top right, that populate the halo. So we see how these clusters, if you like, disperse into the disk and the halo. So this is a good way of sort of working out how the Milky Way sort of builds up from its constituent components. And these are directly measured by having a good idea of the motions and the distances of the objects. So I need to get to the next one. So this is the aberration of light. So this is a sort of little graphic of how the raindrops appear when you're moving along on the train, looking out the window. So the higher velocity that you've got, the more extreme the angle appears to be from the rain coming down. So we can do the same sort of technique looking at quasars. So quasars are really distant objects. They're very bright galaxies, but to Gaia, they look like point sources that would be at cosmologically very significant distances. So effectively, quasars inherently have no parallax. So any motions you see are due to our motion around the center of the Milky Way. And you'll see the sort of the apparent motion of these quasars, this is heavily scaled up, are pointing towards the center, just offset from the center of the galaxy. And this gives us an ability to measure what we call the centripetal acceleration. So this is, we are circular, we're in orbit around the center of the Milky Way. So our sun is going around the Milky Way center. Centripetal acceleration is the apparent acceleration towards the center. Think of if you're in a constant velocity going around in a sort of merry-go-round type on a merry-go-round, and you will get an apparent acceleration towards the center. And we can measure this as a very small number. This is 0.23 nanometers per second at a precision of 16 picometers per second. And this gives the first really accurate, direct measurement of our sun's motion around the center of the Milky Way. That was a nice result from the Gaia DR3. My final couple of slides. What's next? Well, these are moving ahead with their next sort of planning horizon, Voyage 2050. You would have seen that the images I showed you, there were quite a number of regions, especially towards the center of the galactic bulge and also the disk, where dust and so forth obscures our ability to look at the stars in those areas. The dust sort of blocks the optical light. If you go into the infrared, you can sort of see through the dust. So plans are afoot to develop a mission where we have a Gaia-like instrument, but with infrared detectors rather than optical detectors, which means we would be able to probe into the previously hidden parts of the Milky Way and up, mainly the bulge and the disk. But the importance of that is that's where a lot of the stars are. So we'd be observing something like 10 billion objects rather than 2 billion objects. So we'd be probing areas that were hard to reach with Gaia. And that's something to look forward to in the sort of 2040, 2050 timeframe. But we have to plan now. Gaia planning started about 2000, so these are the sort of timescales. Right, if you want to find out more, Gaia data is actually quite fun to just look at and visualize, and there's quite a lot of information out there. So this is the Gaia website. This is cosmos.esa.in/Gaia. That's and got links through to the data releases. So the data releases actually have, if you click the public outreach material link, there's a lot of information there, which is accessible and is quite fun to have a look at. And there's quite a lot of information with some of the release stories, which are nice to look at, some background on some of these things that I've been showing. And this is the next release that I was talking about. So Gaia data, early data release 3 was the astrometry and the photometry. The full data release 3 is the same astrometry. It's the same set of data, but we've got a lot more richer data products coming out, a lot more information about the chemistry, the astrophysical parameters of the samples and so forth. So there's going to be a lot of exciting science coming out with DR3. Which we're going to be putting out just before the first data from James Webb to try to avoid being swamped in the press, as they say. I'll make a note here. If you do a Google search, Gaia Sky, and if you put in Heidelberg, that will probably get you that link. I'll leave it. You can check the video again. But Gaia Sky, out of our colleagues in Heidelberg. They're responsible for some of the outreach material with Gaia. It's a very nice piece of software. You can load up some of these catalogues of nearby objects, for instance, that nearby star, the Gaia nearby star catalogue, and you can visualize it in the ways that you saw some of those videos, movies earlier on. So it's a nice bit of software to use. You can have fly-throughs through the solar system, for instance, and I highly recommend that software. And I think I will finish now with just this, where's the Orion constellation going? What's it going to look like in the coming 400,000 years or so? So we can predict actually where it's going. So let's get the movie going. You'll see the stars moving around. So this is where they are. And some of the brightest stars in the Orion constellation. So bottom right there, you can see that it's going to actually look quite a bit different. If humankind is still on planet Earth in 450,000 years, they will have a significantly different view of the sky, night sky. That was it. Thank you.
Right, if you can unshare your screen, Nick.
Yeah, I'm just
okay.
Do that. Right, there we go.
Thank you. Oh.
All right, I see quite a lot of messages in the chat.
Yeah, I've lost. Oh God, oh well. Yeah. Sorry, I have a technical problem, but I think I've resolved it. I think you can all see me again. Well, that was mind-boggling, the numbers. I think we've got some interesting questions to start the questions, but please don't feel that you have to have used the chat. I'm just going to start with the ones in the chat. And the first one is actually from Alan Grant. You asked right at the beginning of the talk.
All right. How well can we see? Well, those ones, this is, I think, the Milky Way's massive black hole around Sagittarius A or so. We can measure some, but we can't measure the ones really closely. We don't quite have the resolution to get at those. So that one we can't really say much about. I think this understanding of dark matter is slightly related to that. There we are making progress because dark matter influences the stars in the field, and through the motions of the stars we can reveal dark matter, and there's been quite a bit of work on that, and it's probably another topic, but Gaia is having a big impact in that understanding. And through, for instance, we've been able to measure the mass of the Milky Way. Unfortunately, it's the numbers that we get are consistent with other techniques for measuring Milky Way mass. So I don't think we've had a flagship science result in that area yet. Some of that is going to be a DR4 release. I should say that DR4 is the release of the 5-year nominal mission. It takes a long time to process and analyze the data. It's very complex processing, and some of those results will come out in that. And that timescale for that is probably 2025 or so, for a few years yet.
So the dark matter, you'll get the distribution of it. I mean, when you show us how things are moving into the future, is that assuming there is dark matter in our galaxy, or? Well,
it's assuming standard potential. So
okay.
Some of those. So I mean, the shorter term motions, for the nearby motions, it's all clear. Really, a lot of the dark matter issues come up when you're further out into the halo, and one of the attractions actually of going for an infrared Gaia is that you can probe stars further into the halo. So we sort of drop out at a point when interesting things are happening due to dark matter induced impact on orbits, and Gaia just about gets there, sort of at the 25 kiloparsecs, but really you want to be 50 to 100 kiloparsecs, so which you would get with the infrared Gaia version. So it's sort of tantalizing. But it's a bit like some of those arguments for upgrading radio telescopes they used to have in the 80s. You know, if you just go a little bit further, you'll get the rotation curve. Just, you know, and then it'll stop being flat.
Promises, promises.
Yes.
Sorry, I didn't say that. So let's have some more questions. Somebody, Ian. Yes, I think there are people actually having difficulty just scoping the sheer scale of this, the amount of data you're getting, and how it's the numbers are really quite hard to get hold of.
I think Mira's asked a good question. Yeah. You know, what are you trying to do? I mean, some of this is sort of the wonder. Understand really. I mean, I think it's always amazing to me that we've got billions of stars out there. I mean, there's a couple of 100 billion stars in our galaxy. And really, until Gaia, we knew a sort of an accurate sort of 5% distance to about 100,000 of those. I mean, hardly any. And now we can measure to 5% distances to 2% of the stars in our galaxy. And only when you start to do that, you actually really confirm. I mean, we've got an understanding of the model and how stars work and the stellar astrophysics. But once you've got the direct measurement, then you can really be reassured. And really, we've only now been able to sort of say, well, how does a galaxy form? How can you look back? How can you, it's a bit like digging up your history, archaeological digs. Why'd you go and dig? Why'd you dig up the past? Well, we're sort of in many ways digging up the past here to try to understand how we got here in many ways. And I should say that Gaia is really fundamental in our search for exoplanets. It's underpinning many exoplanet searches now. There's going to be some really amazing missions coming up that we're going to be hearing a lot about that are actually going to find Earth types, Earth analogues, places you might want to live around solar type stars. When you just look at the night sky, you look up there and you sort of see, and everything looks more or less the same. How do you know which one of those stars is actually a solar star, which has got a planet around it? Well, Gaia can tell you the sort of stars you want to be looking at with sort of some of these high precision servers. It can also tell you which ones have got the Jupiters running around at sort of like Jupiter distances, and it can enable you to home in on those objects. And I didn't say anything about solar system objects, but we find so many different near Earth objects, asteroids, comets, and so forth. And it's actually quite good at spotting asteroids that we might not want to know about, i.e. the ones that get, give you a blacker dot as it gets closer. So it's a really powerful mission, and it sort of underpins, I think, discovery and the wonder of science, etc.
Okay, there's another question from Gulnara. How many galaxies are there in the whole universe? That's probably a question Gaia doesn't answer, actually.
Yeah, I'm afraid that's one that Gaia doesn't answer, but there's a lot. I think there's an analogy that there are many stars. So you tot up all the stars. I mean, it's billions of galaxies. And if you tot that all up, I think the human body has about the same sort of number of cells. So.
Okay, that's to bring it down to earth for us.
Yeah, just to bring
that was very good.
Just to bring it down to earth. Yeah. I mean,
yes, I don't know if anyone wants to actually ask a question directly. You're very welcome to. There is a facility to raise a hand, which is in the reactions part of the bottom of the screen if you're watching Zoom. So do feel able to do that. But Ian Melville again asked a question for you from the chat. how do you tell if and when stars are extragalactic?
Yeah,
I suppose parallax cannot be determined for stars at the distant parts of our own galaxy.
Yeah, I mean, there I was pointing out some of these high velocity stars, and it's really ones which have got orbits which are non-standard. So you try to track them back, and if they're sort of high enough velocity and they've got vectors which point that are not consistent with being in the orbit of the Milky Way, then we can assume that they've come from outside or out with. So it's basically, and then once we've found interesting candidates, we try to look at their, chemical properties, for instance, metallicities and so forth. But usually it's from the orbital parameters that we can determine. So we found a few which are stars from free floating, the material between galaxies, because there are a few out there. But we also did, yeah.
Okay, there's a couple more questions. Keith Mitchell. Actually, Keith, do you want to ask your question yourself? Okay, I'll read it.
Yes.
It's a naive question. In a Big Bang expanding universe, why and how often do galaxies collide?
Yeah, that's an interesting thing. I suppose if you put a lot of people in a room and then have them moving around and expanding, they still sort of will bump into each other. So I think that's more a cosmological simulation thing, and I'm not sure I've got the answer to that one particularly. But you might think that they're all at a dot and they all move away, and that they wouldn't collide. It's more that they've got motion as well. So that's the sort of bumping into each other. And well, we see, I mean, these events can go on over hundreds of millions of years, really, and we can see the collision, if you like, between the Magellanic clouds, and we can also see actually that our galaxy is stripping stars now off the Large Magellanic Cloud as well. So we can you can see these interactions. I mean, these sort of gravity. It's a pretty vicious thing, actually, gravity. So, and it is one of these things where size matters. The big things tend to gobble up the little things in astrophysics.
Okay, I think that actually brings me to Henry Weatherburn's question. Henry, I can see you on the screen. Do you want to unmute yourself and ask? You have to unmute.
Yeah. Hello. There was a question raised earlier in the chat, and it was about seeing stars near to the black hole at the center of the Milky Way, and I think that was skipped over. Would you like to comment on that, on the black hole?
Most of that work is really, they're having to probe in the infrared. So Gaia doesn't really see that. So we can't really say too much about, it's one of the things that ideas for really accurate infrared astrometry. It's one of the science cases for that. So it's something to look forward to, perhaps for that Voyage 2050 mission. It's one of those infuriating things, if you like, that the galactic center is quite obscured by dust.
Okay, I think we're coming thick and questions still coming, but I think we're going to have to wrap up very soon. Gulnara asked the same question again. I'm not sure you're allowed to do that, but I think it was how many galaxies are there in, if I remember correctly, Gulnara. I shouldn't ask you what you're forgotten. How many galaxies are there in the whole universe? Well, I think you gave us an answer and you could quickly repeat it.
Hundreds of billions.
Yeah.
And,
okay.
It's pretty hard. We're always finding more, and we're searching further and deeper. I think that's one thing. Watch out for James Webb, because that really will probe the ionization. That will really go back further. So they're going to have the Hubble Deep Field, on but factors of 10, hundreds better. So
yeah,
that'd be exciting. But it'll take them a while to do that.
Yeah. But come back in a few years' time. We'll get it for you. Don't worry. It's So I think this is going to be the last question. David Smith, do you want to ask it, David? It's a technical question. Well, I'll read it. In the extrapolation.
Yeah, it's a combination. I think everyone's probably reading it. I mean, we have to put in modelling. So when we're doing the predicting the motions forward, we're having to assume some sort of dynamical model. So it's always a combination of observational and model. But of course, for the nearby objects, it's that modelling is more secure. So the physics is well understood. So they're pretty accurate predictions of where objects will end up.
Okay, Anne Collins asks that we answer Rita's question. I was leaving Rita till last.
Well, not out of surprising finding, yes.
Not out of disrespect, but because you're here, Nick, in part due to Rita.
Yeah,
she's a member of our committee, and she was the person who.
I should have checked that. I mean, it's interesting to see what is the most surprising. So often it's the paper that's got the most citations, and probably the most exciting is that direct measurement of the Gaia Enceladus at the moment. I think this ability to pull out just the general ability to see how many galaxies and smaller dwarf galaxies have been accreted by our Milky Way. We've been actually pretty efficient at sweeping up other smaller galaxies, and that we can actually get direct measures of those, and we can actually, identify populations of stars that have come from those objects. And that's really, really helped us confirm our models of galaxy evolution in a very direct way. So I think that's probably some of the most exciting science that's come out to date. And the one I showed, the direct measurement of motion around the galactic center, that's a very cool piece of science.
Okay, so Rita and Alan Grant were the two people, in fact, who promoted the idea of us asking you, Nick. So I think we're duly grateful to them. They're both members of the Friends Committee. And I'm going to just briefly hand over to Alan, who you met earlier, to perhaps say a few words of thanks. Alan?
Thank you, David. Can you all hear me? Yes, good, super. Well, that was really quite a stunning lecture, Nicholas. Thank you so much. You've convinced us all, I'm sure, why this program of work is well on its way to becoming the most productive scientific space mission of all time, and deservedly so. You've taken us into simulations of, or extrapolations of the data you have 1.6 million years into the future. You've shown us the evidence for the merging of the Magellanic clouds, and you've also helped us to visualize where we are by zooming out by 100 light years from the sun. So all of that in one evening, and the very many numbers you told us is quite staggering. And so I think that the number of stars and bits of information that we've got per euro or per pound must break the records as being the best bargain ever for a space mission. So well done for your part in all of that. It's very impressive indeed. And we'd all, I'm sure, love to meet again when you have some data from 2050, the 2050 mission. But of course, we may not all quite make it that far. But
there'll be lots of really exciting stuff in much shorter timescales, even the summer.
Right. Anyway, thank you so much. Brilliant talk. Thank you again.
Yeah.
You're welcome. It's very nice to be here.
Unmute. Okay. Well, I think, Nick, thank you from myself. It was great to see you again and to hear what you've been up to. I'm going to close now with a couple of reminders. First of all, we're very sad that the visit, members' visit to the Royal Society on the 21st of January has been deferred simply because of COVID regulations. But we're really optimistic that we will get a new date to be confirmed sometime in the spring. So keep reading your emails. The next public lecture, which may be face-to-face at Imperial in South Kensington, or if we're unlucky, will be again Zoomed, is Investigating the Origin of Life in the Universe. It's on Thursday, the 24th of February at 7 o'clock, so a familiar kind of time. And the lecturer will be, in fact, our friend of friends, Mark Sefton from the Earth Science Department. And I imagine there will be a great deal about finding life perhaps on Mars, but I may be extrapolating a little. Anyhow, I look forward to seeing you all on the 24th of February in either 2 dimensions or 3 dimensions. Thank you very much for listening, and thank you very much to Nick once again. And thank you for Alan and Rita for the idea of doing this.